Okay, in section 8.5, we're going to connect loads to this two-phase generator. And let's see, the title of this section is Power Output of a Two-Phase Generator. We'll walk through just like we did with the single-phase generator and observe the output from this two-phase device. And I will just also say that it looks like Zoom is now allowing me to put my own pictures there for background. And this is from, let's see, this is 2021, 2020, didn't go anywhere. This is 2019, and this is, I think, let me get out of the way. This is Loch Leven in Scotland, where I was able to visit last year. And it's a huge freshwater lake and a beautiful, beautiful area. But anyway, let's get back to what we were doing. Okay, working off of this idea that we looked at in section 8.4, the basic construction of a two-phase generator and the voltages that are created from this, the peaks that are 90 degrees apart because the coils are 90 degrees apart. And so let's take that two-phase generator and now let's connect two loads to that generator. This is the load on phase A here, and this is the load on phase B. And what we're going to look at first in this is the designations that we're working with, and those designations again are the voltage is EA1, and the current that is associated with EA1 is IA, or here, and we can see that from this slide that the voltage and the current are in phase since this is a resistive load. And we also see that this voltage is 90 degrees in front of the other voltage that is generated, which we're going to call EB2, or phase B or phase 2, whichever, whichever way we want to think of that. And we can also see from that, that it lags EA1 by 90 degrees. And again, that just mirrors the physical construction of the generator, where physically the coils are 90 degrees apart. So it follows that the generated voltages and currents would be 90 degrees apart from each other. And we also see that with the second coil, that it is resistive load and the current and voltage in it are in phase from our phasor diagram. The instantaneous power that is going to be developed with this generator is going to be the product of the instantaneous voltage times the instantaneous current. And we could, look at graphs of that. But if we look forward here to figure 8.8, we're looking first at phase A, and what we see from phase A is that familiar power output curve, which again, that is the product of the instantaneous voltage and the instantaneous current. And so what we want to notice now here is phase A, and here is phase B. So let's kind of do a little contrast with these, okay? So I'm going to shade these in. Hopefully it's illustrative to you, but I have to admit it's also kind of just fun. But anyway, so here's the power output from phase B here. All right. Now we'll mark this one as B, or we could call this 1 and this 2. And if I combine those, and we'll do this the easy way by not actually doing it. We'll just take his word for it, and we won't do the math that gets us there. But you know, it's pretty obvious, isn't it? If we this peaks 90 degrees before phase B, and now here's phase B peaking, you know, and here at the phase A is at 0. So anyway, we see that consistent across there. But if we looked at the total power output of this, what we would find is that the total power output of the two phases now would be equal to the maximum power of one phase. Well, that worked out pretty good. Look at this. Clean this up a little bit. Oops, I didn't want to take the yellow out, but I won't recolor it. All right, so this is showing the maximum peak power, and this is showing the maximum peak power of the second phase. And if we combine those, we would find that the total power output is now constant. It doesn't pulse anymore. It's like that twin cylinder chainsaw. The power is consistent. It is, look, it's a straight line here. And the value of that straight power output is equal to the peak power of one phase. In the textbook, he says resultant power is constant and equal to the peak power, P sub M, of one phase. In other words, the total power output of the two-phase generator is the same at every instant. As a result, the mechanical power needed to drive the generator is also constant. A two-phase generator does not vibrate, so it's less noisy. And when we talk about noisy, we talk about in terms of electrical noise. And as an important added benefit, it produces twice the power output without any increase in size, except for the addition of the extra winding. Okay, so we got 2 times the power by adding a single coil from the two-phase generator to from the single-phase generator. You remember the power output here, right? We said it was half. You know, we can do the math there. We can do the calculation. We would find out that this is instantaneous power, but the average power for this would be half of the peak. Now we added a coil, and the average power is equal to the peak. So we've doubled the amount of power out of there by just adding an extra winding. Not much cost in doing that. And excuse me, when I say cost, I mean complexity, added expense too. And also, I mean, you wouldn't have to change the size of this generator. I mean, you could use that same stator, right? And you just add an extra coil in there. Okay, so now we've built the two-phase generator. We've looked at the output. We've doubled the power here of this generator by adding a single coil to it.